Good morning, everybody. Welcome back. So, multi-messenger astronomy with gravitational waves is the in thing today. And yes, I know that there's been just one EM counterpart that has been detected so far. It may be a fluke, it might not be, but it's brought in a lot of excitement. The GW sources, the detection of these sources has brought in a lot of excitement in the other wavelength regions in astronomy. And even as this meeting is going on, there's been a lot of excitement trying to search for a black hole neutron star merger event in the other regions. So let me move on and ask the speakers to go ahead. And we'll try to have all the discussions at the end, after all the speakers have completed their talks, so that we have enough time for panel discussion. And I also request speakers to maintain your time so that we have enough time for discussions. Since the meeting is all about discussions, let's do that. So the first speaker is Kenta Hotokezaka. Please.
Thank you very much for inviting me, and thanks to swap the two sessions. And congratulations, Bala, for your big establishment of the career. So I will talk about some overview of multi-messenger astronomy of, in particular, compact binary mergers. So I will not talk on supernova multi-messenger or something like this. So mostly I will focus on what we have learned about kilonova in GW17 and what kind of questions remain after this event and the future, what we can do. And afterglow will be covered by Poonam here, and then gamma ray burst mostly will be covered by Arun later. And because of this is multi-messenger, I will a little bit mention about also the neutrino from the merger. So this is an overview what we saw in GW17. So just after the merger, Fermi and integral detected gamma ray pulse on time scale of second, and we know the radiation we have detected is the energy contains about the energy of 10 to the 47 erg. And from 1 day or half day after the merger to week or two, we saw the kilonova signal, which is mostly thermal spectrum and powered by radioactivity. We call this kilonova signal. It's time, and then total photon that we see is about 10 to the 47 erg. And also later we also saw the afterglow, and this rises up until 100 days, 200 days in radio to X-ray. And also it's surprising that the energy in this radiation is 10 to the 47 erg. So we saw somewhat this kind of energy in the gamma ray and the optical and non-thermal emission. And you can see this is much, much small compared to the energy that radiated in the gravitational wave. But this little amount of energy we can see by the electromagnetic waves. So let's introduce this kind of picture that where the gamma ray comes from. We think this is coming from the shock, just relativistic outflow breaks out from some expanding ejecta. And in order to explain this gamma ray pulse, we need a Lorentz factor at least a few. So mildly relativistic component must exist after this merger. And the somewhat wide angle, we are seeing this event from like 20 to 30 degrees. So we need some wide angle outflow with mildly relativistic velocity to explain these gamma rays. And the kilonova is coming from this bulk ejecta, which is expanding at the subrelativistic velocity, maybe 0.1 c. And the mass in order to explain this emission is about 5% of the solar mass. And the kinetic energy in this subrelativistic ejecta is somewhat huge. And finally, what we see in the afterglow, I mean, this jet coming from the merger interact with the ISM, and eventually it slows down. And this process emits synchrotron radiation. And also this Lorentz factor is what we see is, at least we know the Lorentz factor at the peak is about 4. And, oh sorry, this kinetic energy is wrong, but 10 to the 49 erg, and the angle is not so large. So this is some introduction. Now let me focus more details on the kilonova emission. So this is very basic introduction what I'm talking about. So kilonova is the radioactive energy deposited in the ejector, and then photons that produced by radioactivity diffuses from this ejector. So when we talk the kilonova, we have we imagine the expanding ejector. So this is the edge of the ejector, and then photosphere is somewhere here, and we see spectrum around here. But the photons can diffuse out from the from the photosphere inside the photosphere. So we have photosphere and diffusion sphere. Inside diffusion sphere, we don't see the photons emerging. So as this ejector is expanding, photosphere shrinks and also diffusion sphere shrinks, we see more and deeper ejector. And so the scattering process or absorption process of the photon, usually we are talking about in the context of kilonova is due to the atomic transitions. And for example, this is iron, singly ionized iron. This is the energy level of the iron compared to the R+ element. So you can see very different. So R+ element have usually very dense atomic level structure, which result in the very high opacities. Photons are very difficult to diffuse out from this ejector. So here's what we see in GW70 So these are the bolometric observed luminosity, and I overplot this with this red line is radioactive heating rate. So first striking fact is that the observed light curve is following the radioactive heat. This is particularly special for the R+ elements, that radioactivity goes like declines as a power law. So what we see in the photons is sort of following the R+ heating rate, which is one of the evidence that's supporting this kilonova is powered by R+ elements. And second interesting thing is we see the peak around 0.5 days, and then it declines. It's slower than the radioactive heat. This is because still this phase, the photosphere, diffusion sphere is shrinking. Not all the photons produced inside the ejector don't diffuse out. So we see more deep and deeper. The photons created before start to escape at around 10 days. So this phase, the ejector is still optically thick. And then after 10 days, entire ejector will be optically thin, and then this luminosity is approaching to the heating rate. So the striking point here is we already see some significant fraction of photon at 0.5 days, but the ejector is optically thick until 10 days. So this sort of suggests that there's some low opacity material that photon can easily escape and create the early peak, but we need high opacity material to keep the ejector to be thick until 10 days, which suggests high opacity material. So what does it mean? And also this kind of signature can be seen in the spectrum. This is spectrum evolution of this kilonova. So initially, this is just 1 day after the merger. You can see this is actually very similar to black body. It's very look like black body. It's sort of beautiful, featureless black body signature. And at 5 days and a few days after the merger, you start to see some broad line or some broad signature, but we cannot identify which line really caused this sort of absorption feature in the spectrum. But because of this early blue spectrum and the later infrared spectrum also indicate there is some high opacity around the infrared band. So these two suggest that there are two components, at least. One produce early blue signature, and the high opacity material produce late infrared emission. And if you look at this is Planck mean opacity as a function of the atomic number, sorry. So this should be Z. So this is, you can see this particularly interesting feature around here. This is correspond to the open F shell elements. So this is called the lanthanoid element. The open F shell has very complicated atomic structure that enhance the opacity significantly. For example, but P shell and S shell element don't really contribute to the opacity. So, for example, F shell element really enhance the opacity, and the open D shell elements also enhance the opacity. And the combination of the two, we are thinking now some material is really composed by the low opacity elements somewhere here, and another high opacity material is also exists in order to explain the observed data. So because of there are heavy elements also, not so heavy elements, we are thinking this scenario. So this is, currently we are thinking this is most likely happened in GW70 or 17. So first two neutrons are merged, and then some dynamical ejector is launched at merger. And after this merger, it has had a hypermassive neutron star phase, whereas still some mass ejection is ongoing. But because of the neutrino emission, some light elements are expected to be produced in this phase. But we don't think this is entirely stable, because if it's stable, all the material basically absorb neutrino, and then in the end, most of the material would be around here. So we don't expect the high opacity material when the stable neutron star is formed. So this is, at least we are thinking currently, this is most likely scenario. And this is actually leads interesting, I would say some speculation that combining gravitational wave measurement and the Kilonova measurement, we can constrain the neutron star equation state a little bit more strongly. For example, as you know, gravitational wave measurement alone can tell you tidal deformability, and this is a limit from the gravitational wave measurement. But in order to have this hypermassive neutron star formation, we need some finite value of tidal deformability. If the tidal deformability is too small, that such neutron star merger would immediately form the black hole. So we need hypermassive, we need some large tidal deformability value in order to get the hypermassive neutron star. This is one paper from David Radice that they show the tidal deformability parameter is between these two. And also, in order to get hypermassive neutrons, of course, we need a sort of large maximum mass. So this is one argument, that in order to have hypermassive neutron star formation after this merger, but we don't want to have a supermassive neutron star. This put the upper limit on the maximum mass. So this kind of discussion were done for this GW70 or 70. So now I jump to some questions that we haven't really answered yet. So one thing I told you, this one-day spectrum is a really beautiful black body. But this actually, we haven't understood why this is so black body. Because we think this Kilonova ejector is fully composed of heavy elements which have many lines. Then what is, for example, the spectrum from the radiation transfer calculation? You see some structures due to the line absorption and line emission, but we don't see any such signature. That's sort of, maybe there's some problem in early radiation transfer simulation, or we haven't understand something in the early spectrum. This is one thing we don't know. And another thing, I mentioned there are at least two components, high opacity and low opacity. But there's also one question here. So the light curve that we see is kind of smoothly decline. So here it's t to the -1 and then sharply decline after 10 days. But in general, if you put two opacities, two component model generally predicts this kind of light curve. So low opacity component produce early peak, but later high opacity materials produce something. So usually we expect this kind of structure when you put the two component model. But we don't see such two component feature in the light curve, and also there's no such clear signature in the spectrum. You don't see two component here. So I don't know, maybe the nature really fine-tuned that these two components really connect smoothly and then result in this smooth light curve. But this is also some question about the modeling that we have so far. Okay, and then future, what we really want to see is if we see the merger with different masses, what kind of difference in the electromagnetic counterparts that we are really looking for. For example, if there is supermassive neutron star, we expect this is magnetized and EM radiation would be very powerful in this case. And also black hole neutron star merger, in some cases we expect a huge accretion disk or dynamical ejecta. But it's all depends on the mass of the merging object, so it will be very helpful for astronomers to know the masses before we decide what object will be followed up. Okay, so it's really this observation, this light curve and spectrum observation are beautiful, but we haven't really identified any elements here. So there's many evidence that there are heavy elements synthesized in this merger, but we don't have a very strong confirmation of the heavy element production. So now let me talk about how we can identify the heavy element in the signal. So one way to look at is some signature of alpha decay elements and the fission. This alpha decay can contribute kilonova heating significantly, actually, and this alpha decay elements is coming from mass number is sort of high, like 220 to 225. And this actually can be larger than the beta decay heating rate. So then in that case, we expect some excess in the heating rate at a later time, about 10 days and 100 days. And also fission may contribute to this heating rate significantly. For example, californium is one of the most promising super heavy elements that with half-life of 60 days can produce some excess in the light curve. So this is one way to identify, still indirect, but identify the heavy elements. And another way is, unfortunately, GW70 we couldn't see like entire optical infrared spectrum at 40 days after the merger, because 40 days, the photosphere completely shrinks, and what we see is all emission lines from the heavy elements. So we call this phase as a nebular phase. So nebular phase, we expect all these emissions coming from the atomic emission. So this is one example that I calculated recently. This is neodymium, pure neodymium Kilonova nebula. So you can see this is some rich feature in the spectrum, mostly in the near infrared band. And if we can see this spectrum at 40 days, 70 days, and maybe we will be able to identify the lines of heavy elements. And actually this can be done by JWST even at 200 megaparsec. And one thing also interesting is nuclear gamma ray, of course. So if we can detect nuclear gamma rays, we can even tell you what kind of isotope exists in the merger ejecta. But this is really difficult. And so far we have some upper limits from NuSTAR, which is few orders of magnitude still higher than what we expect. So this is extremely difficult, but it will be the ultimate proof of this R-plus nuclear synthesis. Okay, I will skip the jet physics, but I want to mention, so because of the afterglow light curve and also the motion of the afterglow emission, we can really tell you what is the energy in this jet that we see in the afterglow, and also the viewing angle to the afterglow. So because of the gravitational wave constraint on the Hubble constant, we generally degenerate with this viewing angle uncertainty. So we can sort of resolve this information using afterglow light curve and also the VLBI superluminal motion. And a little bit we can improve the posterior distribution of the Hubble constant. Of course, this method depends on the jet physics, so we have to improve the jet the understanding of the jet if we want to improve this with more future events. Okay, I will skip this. And the last thing not this is the last thing, but I think Arun will talk about GRB, so I will skip this. So the last thing I want to tell you is the high energy neutrinos. So this is so detection of the neutrinos from merger is not really promising. First of all, there's a lot of thermal neutrinos are emitted after the merger because of this is very hot and dense material there. But it can be detected up to 10 megaparsec, even if we have a hyper Kamiokande. So one possibility is to see high energy neutrino by ice cube. So this is one way to do it. So there is a jet propagating inside the ejector. There is some shock inside the jet. So in this shock, there's some suggestion that the particle acceleration occurs. And if protons are accelerated, then high energy neutrinos are produced. So this is one possible way to do it. And at 40 megaparsec, ice cube potentially will be able to detect 2 neutrinos at the TeV. But it's I would say it's not hopeless. We have some chance to see high energy neutrinos. But the question is really this particle acceleration inside the jet would work or not. And if we see another nearby event, we will be able to start to put the limit what acceleration efficiency, and also we have some chance to see the ice cube neutrinos. And I think I stopped here. Thank you very much.